Hey friends, this is Vidhan. Welcome you to my channel. Today we will see some concepts of op-amp and we will see some points of operational amplifier circuit, and these points can work as the tricks for you for solving CSI net problems on op-amp and also some other op-amp problems. These tricks are basically about how to take the input voltages and how to take the voltage drop across the resistors and also the output voltages. Especially here we will see the circuits for open loop, that means operational amplifier circuit for open loop, and we will see the same circuit with the feedback, and we will see these points, the points of discussion that I'm talking about. We will see for open loop as well as for the same circuit with feedback. First of all, today let us take the inverter. Actually, with open loop the basic circuits are inverter, non-inverter, differential amplifier. So first of all, today take inverter, and let's take open loop. Now how does a inverter look like in open loop configuration? It's like negative, positive, it is grounded, input voltage. Now input voltage could be AC, could be DC, because it is a versatile device. It can amplify AC signal as well as DC signal. So for now we take AC signal, and through a resistor it goes to input terminal or resistance R1. Let us take R1. Now this is also grounded, and the output also goes through a load resistor and ground. Now this load resistance can be a bulb, this could be a speaker, or this could be any gadget that you want to drive using the output voltage. Now always know that plus 15 volt, minus 15 volt are there, because without this biasing the operational amplifier cannot work. This is inverter circuit with open loop, because I am not giving a feedback to the input. Okay, either this way or this way, I have not given a feedback. So this is open loop configuration. And why inverter? Because I have given the input signal to the negative input terminal. This is also called inverting terminal. And what happens, the output signal that we will get will have a phase change of 180-degree with respect to the input, and that's why we call it inverter. Okay, now one thing, the first point that I was talking about is, at this point the voltage is 0 because it is grounded. Now at this point the voltage will not be 0. This is the point. In open loop the virtual grounding concept is gone. The virtual grounding concept is not applicable. What I am saying is, in virtual grounding concept, whatever is the voltage at positive terminal happens to be the voltage at the negative terminal. But in case of open loop, you forget about this. This is one trick. So what would be the voltage at this point? It will not be equal to this voltage. And what would be the voltage actually? The voltage would be whatever is the voltage. Suppose this is V input I give here, this voltage. This will also be V input. This is the trick. And also one point, the second point is that generally we know that if there is a voltage and if there is a resistor ahead, then this voltage will drop across the resistor, and the voltage at these points, let us take at this point or at any of these points, should be less than this voltage, because there should be a drop. Since there should be a drop across resistor, so this voltage should be less than the input voltage, but it is not the case in open loop. The voltage given here is the voltage at this point. Okay, and why it happened so that it did not drop across the resistors? very high input, sorry, very high input resistance, infinitely high, that means very huge input resistance, and because of this voltage did not drop. Since it is voltage operational amplifier, it is voltage amplifier, okay, our signal is voltage. There are several configurations. We may have current signal, we may have voltage signal, but now our voltage signal is the voltage signal, so we don't want to lose it. We can't afford to lose the voltage signal, and that's why we have given infinite input resistance here, so that it cannot drop here. What I mean is, actually this is about voltage divider rule. If I tell you the voltage divider rule, you will get the point. We know that, let us suppose a circuit, this will be called voltage divider circuit. You are already aware about it. This is 2 ohm, this is 4 ohm, and suppose this is 12 volt plus minus. Tell me one thing, that what is the current in this circuit? Always remember that in a circuit, current is always a single current in the circuit. Now the current is I is equals to V by R, and R actually are equivalent. So 12 by, what is the equivalent resistance in the circuit? That is 6 ohm, 2. That means I is equals to 2 ampere. Then in the whole circuit, a single current runs, and that is 2 ampere. At this point 2 ampere, at this point 2 ampere, at this point 2 ampere, through through this 4 ohm 2 ampere, at this point 2 ampere. In the whole circuit, it runs a current of 2 ampere. Now, what is the voltage at this point? 12 volt. At this point, 12 volt. At this point, 12 volt. But at this point, it is 8 volt. Why? The voltage has dropped. What I am saying is, voltage drop. V is equals to I into R. Now, this V is, this is the Ohm's law obviously. But now, this V is the amount of voltage drop across this resistor. Now, V is equals to I into R. I is 2 and R is 2. 4. So this resistor has dropped 4 volt. Now here it was 12 volt. At this point it was 12 volt. It has dropped 4 volt. Now at this point what is the voltage? 8 volt. Very important. This is the voltage division. Now if you take a voltage terminal from here, then it will give you 8 volt point. But it is not necessary now. So for here, for now, it is 8 volt point. Now what is the voltage drop across this resistor? Now V is equals to I into R. And I into R is what? Now 2 into R is 4 ohm and it is 8 volt. See, across the resistor, this 8 volt drops. And what it becomes? It becomes what? Here. That means 0. Suppose the voltage difference just gets lost. So you can see at this point it is 12 volt. 4 volt drops across 2 ohm and it becomes 8 volt here, and 8 volt drops across 4 ohm and it becomes 0. That means whatever is the voltage difference, that must drop across the equivalent resistance. This is also one rule. So what two rules are there? That a single current flows through the circuit, a single equivalent current for equivalent resistance, and the voltage difference that is given through the across the resistors, that voltage difference finally become 0 after successive droppings. Here 4 volt dropping and here 8 volt dropping. Okay. Now you must be aware of a formula that voltage drop can also be given by a different formula I am talking about. The voltage drop at this point is 12 into 2 by 2 plus 4. That means 12 into 2 by 6, 4 volt. See, I had told you that across this 4 volt will drop, and also this is called the voltage divider formula. The voltage drop across this resistor, that means across 4 ohm, is 12 into this resistance by all the resistances added. 12 into 4 by 6. 4 into 2, 8. I had told you by that rule. So whatever rule you use, you get it. But actually there is voltage drop. The voltage has dropped here, and it has now only 8 volt at this point, and this 8 volt will drop across this. Now, in regard to the operational amplifier, now you have to be a little patient that what is the case in our operational amplifier. We have told that here there is an infinite input resistance, and because of this infinite input resistance, the voltage drop across this resistance is almost zero. Why are we saying this? Now let us take, now again let us take a resistance R. R is suppose 2 ohm. Okay, even if not 2 ohm, let us take a big number. Let us say it is 10 kilo ohm. Okay, 10 kilo ohm, let us suppose, and this is one resistance, and here are infinite resistance. Infinite resistance means, let us suppose it is 10 mega ohm. Okay, okay, it is 10 mega ohm and it is 10 kilo ohm. So we have supposed it, and we have a voltage, that voltage is suppose 100 volt. Now what is the voltage drop across this resistance? The voltage drop across this resistance, that voltage divider formula we will use 100 into this 10 into 10 to the power 3 by 10 into 10 to the power 3 plus 10 into 10 to the power 6, isn't it? So what is this? This is 100 into, this is 10 to the power 4 by, this is 10 to the power 4 plus this is 10 to the power 7. Okay, now from here you can see that this is 10 to the power 7 plus 10 to the power 4 is what? It is what? We can do one thing, that it is 100 into 10 to the power 4 by, let us take 10 to the power 4 as common. So we have 1 plus 10 to the power 3. Okay, it just cancels out. So 100 by 10 to the power 3 is 1000. That means 1 by 10, 0.1 volt. So 0.1 volt drops across this resistor. Can you imagine? 0.1 volt has dropped across this resistors. What I have done, I have taken two resistances. One is very low, not very low, but at least we have taken a lower resistance, and one is a very high resistance, 10 mega ohm. Okay, like here a resistance is a small resistance, and here I suppose a infinite resistance. Now according to the voltage divider rule, that voltage drop across this point is 0.1 volt, and since it was 100 volt, so what is the voltage at this point? At this point we have 99.9 volt. You understand? So actually across this resistance no voltage has dropped, we may assume. Now let us say that what is the voltage drop across this resistance. Now the maximum voltage will drop across this resistance. We can see it, we can check it, and we will find that finally that 99.9 volt will be the answer, because across this resistance, this we know that the whole 100 volt should drop across the whole resistance. So if only this much has dropped across this resistance, then the rest must drop across this. So this means across this resistance a very little volt will drop, and what will be left is just equal to or equivalent to the input voltage. So at this point the voltage will be same to the input voltage, and since there is no feedback circuit, so the voltage at the positive terminal will not be voltage at the negative terminal because there is no feedback circuit. So the virtual grounding is also not happening here. So these are the two things that you have to keep in mind. Okay. Okay, now the same circuit, let us see the inverter now with feedback. Now how does this inverter circuit look with feedbacks So here we have the amplifier negative positive V output, and positive is again grounded and negative similar to the previous one, a resistance, and it goes there. But now what we do, we give a feedback through a resistor to the negative input terminal, and that is why it's called negative feedback. Now you may ask, why always I talk about negative feedback, and why only the negative feedback? I could give the feedback through here and here. Actually, positive feedback is used for the oscillator circuit because we want a stable output. If I give the negative feedback, then I get a stable output and the output will not be oscillating. But positive feedback, if I give, that will be the oscillating output, which is not required for this case. Okay, that is why generally all the applications of operational amplifier uses the negative feedback circuit. Okay, let us see what happens here. Here R1, it is V input, it is RF. Okay, now one thing is that the output, let us write down the output. Here the output is simply A. Suppose the input, the gain, open loop gain is A, then A into V input. This is the output, and since the input has been given at a negative terminal, so it is negative. Simply this is the output for open loop. Okay, here the output is, I'm directly writing it directly. I'm not deriving this output. This can be derived using KVL at this point, KCL, sorry. Okay, by the way, what is the output? Just I'm writing it. It is minus RF by R1 into V in. This is the output for feedback circuit. This is inverter, this is also inverter. This is with the feedback circuit and the feedback resistance RF, and this is the output voltage, you remember, and this is the output voltage. Okay, now the 2 points that I was talking about. So let us take the first point. Now I talked here that here the voltage is 0, but at this point the voltage is not 0. Now since there is a feedback circuit, what is the voltage at this point? It is 0, I can say, because it is grounded. Now at this point also the voltage will be 0. This is the concept with feedback. Even if you can see that the voltage is there, input voltage, but at this point the voltage will be 0. That means the feedback circuit works in such a way that it wants to make this voltage equal to whatever the voltage at this point. So feedback circuit, that means virtual grounding, and this concept that this voltage equal voltage concept comes from the feedback, and this concept is known as the virtual grounding concept. So it came into effect, virtual grounding concept, and when we use this effect and use the laws, then we find this output. Remember this. And why the voltage could be 0 here? Because now V in, why at this point the voltage is now not V input? Because now voltage can drop. Why? Because now the resistors, here is a resistor and it is bypassing this input voltage. This input voltage is bypassing this internal infinite resistance, but it is going through this way. That means it is encountering little resistances. So across this resistance there will be a big voltage drop of this input. A considerable voltage drop you will see across this resistor, because it is now going to be this circuit and it bypasses this. Okay, so this is one point. So whenever you see open loop, then you just have to think that whatever is the voltage given here is the voltage at the input terminal. But when you see the circuit with feedback, then you have to think whatever you have the given, whatever voltage you have given here is not the voltage at this point. At this point the voltage will be the voltage what is at the positive voltage. Suppose if I use a voltage here, it is suppose 2 volt, 2 volt, then at this point it is actually 2 volt. Suppose 2 volt I have used here, so at this point it will be 2 volt, then at this point also it will be 2 volt by virtual grounding. Actually what happens is near to 2 volt, not exactly 2 volt, but you have to suppose that this is 2 volt. This is the concept. So I think you understood it, and you have to remember these two things. And later in later videos we will derive this equation, how to get it. Here there is no derivation actually. You just give the gain times input voltage and you will get the output, but here a derivation gives us the output, and here Rf by R1 is the gain. Okay, similarly for non-inverter circuit we can see for open loop and the same non-inverter circuit with the feedback, and same in the same way the differential amplifier with open loop and differential amplifier with feedback we will see in later videos. And for this there is one concept, that is the voltage divider role, that is coming into play. And here I said that virtual grounding is not actually working. You have to take the voltage, whatever the voltage in the input, but here the voltage actually is whatever the voltage at the positive terminal. That means virtual grounding is coming into place. Okay, thank you.